The solar system is 4.6 billion years old. We have been studying it seriously for less than 500 years, with instruments capable of reaching it directly for less than 70. And in that astonishingly short window of observation and exploration, we have made a discovery that should give every one of us pause. The more closely we look, the stranger it gets. Not in a poetic sense, in a strictly scientific one. We have found a moon that may have a liquid ocean larger than all of Earth's oceans combined, hidden beneath kilometers of ice. We have found a planet where it rains diamonds, a world so cold that its atmosphere freezes and falls to the ground as snow when winter comes, and winter lasts 42 years. A region at the solar system's edge where objects travel in orbits so strange that the only explanation that fits the data is the gravitational influence of a planet we have never seen. These are not speculations. They are the findings of peer-reviewed planetary science, published in the journals, confirmed by multiple instruments, and still, in the most interesting cases, not fully explained. This documentary is about those mysteries, not the ones with easy answers, the ones that keep planetary scientists awake at night, debating at conferences, redesigning spacecraft missions to get better data. The mysteries at the heart of the place we call home, the solar system, that we are only now beginning to have the tools to properly investigate. We will travel from the innermost planet to the outermost reaches of the Oort cloud. We will visit worlds that should not exist by any model we currently understand. We will ask questions that the data demands and sit with answers that are still being formed. The solar system is not a solved problem. It is an ongoing investigation. And what we have found so far is more astonishing than anyone predicted when the investigation began. Let's start at the center with the object that everything else orbits, and discover that even the sun, which humanity has observed continuously for thousands of years, still holds a mystery that no one has solved. The sun's impossible corona. ... Here is a fact about the sun that every physicist who hears it for the first time does the same thing. They frown and ask the question to be repeated. The surface of the sun, the photosphere, has a temperature of approximately 5,500 degrees Celsius. This is very hot. It is hot enough to vaporize every material known to science. But the sun's outer atmosphere, the corona, the thin, wispy halo of plasma that extends millions of kilometers into space and is only visible from Earth during a total solar eclipse, has a temperature of between 1 and 3 million degrees Celsius. The corona is 200 times hotter than the surface directly below it. This makes no physical sense under any ordinary understanding of heat transfer. If you move away from a heat source, the temperature should drop, not rise. If you walk away from a campfire, you get colder. The further from the fire, the colder you get. This is not a principle with exceptions. It is thermodynamics. And yet the sun violates it, or appears to, in a way that has puzzled physicists since 1939, when Swedish physicist Bengt Edlund first established through spectroscopic analysis that the corona was millions of degrees hotter than the surface. 87 years later, no consensus explanation exists. Two leading hypotheses are on the table, and both have partial observational support, but neither has been decisively confirmed. The first is wave heating. The sun's surface is in constant, violent convective motion, with enormous columns of hot plasma rising and falling in patterns called convection cells. This motion generates waves in the magnetic field lines that thread through the sun's atmosphere, alpha waves that carry energy outward from the surface into the corona, where they deposit it as heat. The Parker Solar Probe, which has been flying closer to the sun than any previous spacecraft, has detected these waves and confirmed that they carry more than enough energy to heat the corona. The question is exactly how and where that energy is deposited, and why the corona is heated to such extreme temperatures rather than simply receiving a warm current that dissipates with distance. The second hypothesis is nanoflare heating. The sun's magnetic field lines are constantly reconnecting in the corona, snapping and rejoining in a process that releases energy. Astrophysicist Eugene Parker, after whom the solar probe is named, proposed in 1988 that millions of tiny, individually undetectable reconnection events, nanoflares, could collectively heat the corona to the observed temperatures through a cascade of small energy releases. The challenge is that nanoflares are, by definition, too small for current instruments to detect individually, making this hypothesis difficult to test directly. The corona heating problem is not merely an academic puzzle. Understanding it would significantly improve our ability to predict solar flares and coronal mass ejections, the enormous bursts of charged particles that the sun periodically fires into space and that can disable satellites, disrupt power grids, and in extreme cases, threaten astronauts beyond Earth's protective magnetic field. The sun is the engine of the solar system, and we still do not fully understand how its engine's exhaust gets so hot. Mercury's impossible ice. Mercury is the closest planet to the sun. Its surface temperature at the equator can reach 430 degrees Celsius in daylight, hot enough to melt lead, permanently, stably, perhaps billions of years old. Water ice sits in permanently shadowed craters near Mercury's poles. Craters whose rims are tall enough and Mercury's axial tilt so small, just 0.034 degrees, making it the most upright planet in the solar system, that their floors have never been touched by sunlight since the craters formed. In these permanent cold traps, temperatures can drop to minus 200 degrees Celsius, and there the ice sits, stable and ancient, on the surface of the planet closest to the sun. The ice was first detected by radar observations from Earth in 1991, confirmed by the Messenger spacecraft in 2011 and 2012, and has since been estimated to total between 100 billion and 1 trillion tons of water ice. This is not a trace detection. It is a substantial quantity of water, and its presence on Mercury raises immediate questions about how it got there. The leading explanation is cometary and asteroidal delivery. Over the course of Mercury's history, comets and water-bearing asteroids have impacted the planet, delivering water molecules to the surface. On most of Mercury's surface, these molecules would have immediately evaporated in the extreme heat. But molecules that migrated, perhaps through a series of hops across the sunlit surface, to the permanently shadowed polar craters, would be stable, accumulating over billions of years into the deposits we now detect. What makes the Mercury ice particularly interesting is not simply its existence, but what it might tell us about the origin of water on all the inner planets, including Earth. If water-bearing impactors could deliver ice to Mercury and have it preserved there, they could deliver water to any inner planet where cold traps exist. The water in Earth's oceans, and by extension, the water in every living cell on our planet, may have arrived through a version of the same process that put ice on Mercury. The closest planet to the Sun holds a clue about the origin of life's most essential molecule. There is also a layer of what appears to be organic-rich dark material overlying the ice in some polar deposits, detected by Messenger's neutron spectrometer. The identity and origin of this dark layer is not fully established. The leading hypothesis is that it is carbonaceous material delivered by the same comets and asteroids that brought the ice. But the specific chemistry of this material has not been measured directly, and whether it contains any prebiotic organic compounds of interest remains an open question that future Mercury missions may be able to address. The planet that ran in reverse. Venus and Earth are almost twins in size, mass, and distance from the Sun. By every planetary formation model we have, they should have evolved similarly. Earth became a planet with liquid oceans, a nitrogen-oxygen atmosphere, and life. Venus became a hellscape of 465-degree surface temperatures, a crushing atmosphere 90 times denser than Earth's, composed primarily of carbon dioxide and clouds of sulfuric acid. Something went catastrophically wrong for Venus, or it was never going to work out for it, and we do not know which. The mystery of Venus begins with a fact so strange it took decades for scientists to accept it as real. Every planet in the solar system orbits the Sun in the same direction, counterclockwise when viewed from above the solar system's North Pole, a consequence of the conservation of angular momentum in the rotating disk of gas and dust from which the planets formed. Most planets also rotate in the same counterclockwise direction. Venus rotates clockwise, making it one of only two planets with retrograde rotation, the other being Uranus, which rotates on its side for different reasons. The Sun rises in the west on Venus and sets in the east. A day on Venus, one full rotation, lasts 243 Earth days, longer than its year of 225 Earth days. How Venus ended up rotating backward is genuinely unknown. Two main hypotheses exist. The first proposes that Venus suffered a massive collision early in its history that reversed its rotation, similar to the collision proposed for why Uranus is tilted. The second proposes that Venus's retrograde rotation emerged gradually from tidal interactions with the Sun and from atmospheric thermal tides, the heating of the atmosphere on the sunlit side creating pressure differences that, over billions of years, could torque the planet into its current unusual spin state. Both hypotheses have been modeled mathematically, and both can produce the observed outcome. Distinguishing between them requires better data about Venus's internal structure and the history of its surface than we currently have. The bigger Venus mystery is the runaway greenhouse. Venus and Earth presumably started with similar water inventories. Venus today has almost no water. The extreme heat and the intense ultraviolet radiation from the Sun split any water vapor in the upper atmosphere into hydrogen and oxygen, with the hydrogen escaping to space. Earth retained its water. The difference appears to be distance. Earth is just far enough from the Sun that water condensed into liquid oceans before the greenhouse effect could run away, whereas Venus was just close enough that the early warming from a slightly brighter young sun prevented liquid water from persisting, allowing CO2 to accumulate in the atmosphere and the greenhouse effect to intensify until the ocean evaporated and the remaining water was lost to space. The margin between Earth's fate and Venus's fate may be very thin. Some climate models suggest that if Earth were only 5 to 10% closer to the Sun, it too would have undergone a runaway greenhouse. Venus is sometimes described as Earth's evil twin, but it is more accurately Earth's cautionary mirror, showing what happens to a world just slightly less lucky in its position around its star. Venus currently has 2 spacecraft on their way to study it more closely. The ESA Envision mission and NASA's Veritas mission are both designed to map Venus's surface at high resolution and understand its geological history, answering the question of whether Venus ever had oceans, and if so, when and how they disappeared. The answers will have direct implications for understanding the habitability of Earth-like planets elsewhere in the galaxy. The moon that should not exist. The moon is familiar. It is also deeply strange, and the theory of its origin, while now widely accepted, remains one of the most dramatic origin stories in planetary science. The moon is too large. Compared to Earth's size, the moon is about 1/81st the mass of Earth, an enormous fraction for a natural satellite. Most other moons in the solar system are tiny compared to the planets they orbit. Mars's moons, Phobos and Deimos, are asteroid-sized pebbles. Even the moons of the outer planets, though some are enormous in absolute terms, are tiny compared to their host planets. The Earth-Moon system is, proportionally, almost a double planet. The Moon's composition makes this strangeness even more acute. The Moon has almost no iron core. It is predominantly mantle material, silicate rock that closely matches the composition of Earth's own mantle. It is not a captured asteroid, which would have a different composition. It is not a body that condensed independently from the solar nebula alongside Earth, which would have a more primordial composition, including more iron. It is made of Earth, specifically of the outer rocky layers of early Earth. The giant impact hypothesis, proposed in 1975 by William Hartmann and Donald Davis, and independently by Alastair Cameron and William Ward, proposes that approximately 4.5 billion years ago, a Mars-sized protoplanet called Theia struck the early Earth at an oblique angle in a glancing collision that ejected an enormous amount of Earth's mantle material into orbit. This material, heated to vapor and plasma by the impact, coalesced in orbit over a period of perhaps 100 years into the Moon. This hypothesis explains the Moon's composition. It is Earth's mantle. It explains the Moon's lack of iron. The iron from both Earth and Theia had already sunk to the cores of both bodies before the impact. It explains the angular momentum of the Earth-Moon system. And it explains why the Moon is so large. It formed from the direct material of a planet, not from a fragment of space debris. What the hypothesis struggles to explain, and what has become the focus of intense recent research, is the compositional similarities between Earth and the Moon that are almost too perfect. When geochemists measure the isotopic ratios of oxygen, titanium, silicon, and other elements in lunar samples returned by the Apollo missions, they find that the Moon's isotopic composition matches Earth's almost exactly, to a precision of parts per billion in some measurements. This is a problem because Theia, being a separate body that formed in a different part of the solar system, should have had a different isotopic signature from Earth. The impact should have mixed Theia's material into the Moon, along with Earth's, producing a Moon with an isotopic signature intermediate between Earth and Theia. Instead, the Moon looks like it is made entirely of Earth. Several resolutions have been proposed. Some models suggest that Theia happened to form in a region of the solar nebula with a nearly identical isotopic composition to Earth. Some suggest that the impact was more energetic and complete than the standard model assumes, vaporizing both Earth's outer layers and all of Theia, and creating a well-mixed magma ocean from which the Moon condensed. Some propose that the post-impact Earth-Moon system rotated much faster than today, and was coupled in a resonance that allowed material to flow freely between the two, homogenizing their compositions before the Moon moved to its current distance. None of these solutions is fully satisfactory. The Moon, the most studied extraterrestrial body in human history, visited by 12 human beings over the course of 6 missions, is still telling us things about its own origin that we cannot explain. Mars and the mystery of the missing ocean. 4 billion years ago, Mars was a different world. The evidence is written into its surface in forms that cannot be misread. Valleys carved by flowing rivers, lake beds filled with ancient sediments, deltaic formations where rivers met standing water, minerals, clays, carbonates, sulfates that only form in the presence of liquid water, and a northern lowland basin covering about 1/3 of the Martian surface that many researchers believe was once a shallow ocean. Mars had water, a lot of it. Some estimates put the total volume of ancient Martian water at enough to cover the planet to a depth of several hundred meters, if distributed uniformly across the surface, a global ocean shallower than Earth's, but genuinely oceanic in scale. Within perhaps 500 million years, Mars transitioned from a planet with liquid water to the cold, dry, near-airless world we observe today. The atmosphere thinned from something thick enough to maintain liquid water at the surface to the current pressure of less than 1% of Earth's, insufficient to maintain liquid water even at the equator in summer. The water froze into the polar ice caps and the subsurface permafrost, or escaped to space as the atmospheric pressure dropped, or was locked into minerals and rocks through chemical weathering. The oceans dried, the rivers stopped running, and the planet died. The central mystery is not that this happened. It is why it happened so completely and so quickly in geological terms, and whether it was truly inevitable from Mars's starting conditions, or whether Mars was, for a brief window of geological time, a place where life could have begun. The leading explanation for Mars's atmospheric loss centers on its magnetic field. Early Mars appears to have had a global magnetic field, similar to Earth's, generated by convection in a liquid iron core. Earth's magnetic field is what protects our atmosphere from the solar wind, the continuous stream of charged particles flowing out from the sun. When those particles strike Earth, they are deflected by the magnetic field before they can strip atmosphere away. Mars lost its global magnetic field approximately 4 billion years ago. Geologists can see this in the pattern of magnetized and non-magnetized rocks on the Martian surface. And without that protection, the solar wind began systematically eroding the atmosphere, carrying charged particles from the upper atmosphere out into space. NASA's MAVEN spacecraft, which has been studying Martian atmospheric escape since 2014, has measured this loss process directly, calculating that Mars loses approximately 100 grams of atmosphere to space per second even today. 4 billion years ago, when the sun was more active and the solar wind more intense, the loss rate would have been far higher. What remains most tantalizing about the Mars story is the subsurface. In 2018, the MARSIS radar instrument on the Mars Express orbiter detected a signal beneath the south polar ice cap consistent with a subglacial lake of liquid water, approximately 20 kilometers wide and a depth of about 1.5 kilometers. The finding is controversial. Subsequent analyses have proposed that the signal could also be produced by a specific type of volcanic rock with high radar reflectivity, but it has not been definitively ruled out. If liquid water still exists beneath Mars's surface today, the question of whether it could still support life in some form becomes one that only a drilling mission to that location could answer. Perseverance rover is currently collecting rock and soil samples from the floor of Jezero Crater, an ancient lake delta, for eventual return to Earth by a joint NASA-ESA sample return mission. Those samples may contain, preserved in the ancient lake sediments, the chemical or even biological signatures of a Martian biosphere that existed 4 billion years ago. If they do, everything about how we think of life in the universe will change. If they do not, the absence itself will be informative, constraining the conditions under which life can or cannot begin, with implications for every other potentially habitable world in the galaxy. Perseverance has already changed the Mars story in ways that go beyond the sample cache. Its MOXIE instrument, the Mars Oxygen In Situ Resource Utilization Experiment, successfully produced oxygen from the Martian atmosphere's carbon dioxide, demonstrating for the first time that human visitors to Mars could potentially produce breathable air and rocket propellant from local resources rather than carrying it all from Earth. Perseverance's Ingenuity helicopter made the first powered flight in the atmosphere of another world in April 2021, a milestone comparable in principle to the Wright brothers' first flight, and continued to operate for nearly 3 years beyond its originally planned 5-flight demonstration, fundamentally changing how NASA thinks about aerial reconnaissance on Mars. The Mars we are exploring is not simply the Mars we imagined. It is stranger, more varied, and more interesting, with perchlorate salts that would be toxic to Earth life, but that some Earth bacteria have evolved to metabolize, with seasonal variations in methane concentrations in the atmosphere that are still not explained by any abiotic chemistry, and that several research groups have proposed as potentially biological in origin, and with a subsurface that radar sounding has revealed to be layered in ways suggesting complex geological and hydrological history extending far beyond the simple wet-to-dry transition story. Mars is not a dead world. It is an incompletely understood one, and the incompleteness is the most interesting thing about it. Jupiter's storm that outlived civilizations. The Great Red Spot on Jupiter is the most famous storm in the solar system. It is a persistent anticyclonic storm, an area of high atmospheric pressure rotating counterclockwise in the southern hemisphere that has been observed continuously since at least 1831, when observations became reliable enough to track it, and possibly since 1665, when Giovanni Cassini described a permanent spot in roughly the same location. If the 1665 observation is the same storm, the Great Red Spot has been active for at least 360 years. Its longevity is the first mystery. Most storm systems on planets with atmospheres are driven by temperature differences between air masses, and they dissipate when those temperature differences equilibrate. The Great Red Spot should have dissipated centuries ago by this logic, yet it persists. The reason appears to be that Jupiter has no solid surface to drain energy from the storm system. On Earth, hurricanes weaken when they make landfall because the friction with the solid surface disrupts the circulation. Jupiter's storm extends from its visible cloud tops down thousands of kilometers into a gas giant atmosphere with no solid surface to interact with, allowing the vortex to persist and even to feed on smaller storms that it absorbs when they drift within its gravitational influence. But the Great Red Spot is shrinking. In the 19th century, it was estimated at 40,000 kilometers wide, wider than 3 Earths placed side by side. By the mid-20th century, it had reduced to about 25,000 kilometers. Today, it is approximately 10,000 to 12,000 kilometers wide, still larger than Earth, but clearly in a multi-century decline. It is also becoming more circular as it shrinks, losing the elongated oval shape it maintained for most of the observational record, and its color has changed from the deep brick red of earlier centuries to a more salmon or pale orange in recent decades. Some models predict it will become a circular vortex, a red circle within a generation. Some predict it will eventually dissipate entirely. No one knows which outcome is correct, or exactly what is driving the shrinkage. The color of the Great Red Spot adds another layer of mystery. The reddish-brown pigmentation appears to come from complex organic and inorganic compounds, possibly acetylene, benzene, and phosphine derivatives, that form when ammonia, hydrogen sulfide, and other atmospheric gases are exposed to ultraviolet radiation from the sun high in the atmosphere. The exact chemical identity of the chromophores responsible for the color has not been definitively established. Laboratory simulations have produced red-brown compounds from Jovian atmospheric gases under UV irradiation, but replicating the precise color of the spot has proved elusive, and the chemistry of Jupiter's upper atmosphere remains an open field. Below the cloud tops, Jupiter becomes increasingly strange. The Juno spacecraft, which has been orbiting Jupiter since 2016 and making the closest passes of any probe to the planet's cloud tops, has found that Jupiter's famous banded structure, the alternating light zones and dark belts that are visible even through a backyard telescope, extends much deeper into the atmosphere than expected, with the jet streams driving these bands reaching depths of 3,000 kilometers or more. The bands are not simply a surface phenomenon. They are expression of something happening deep in the planet's interior. Deeper still, at pressures thousands of times greater than Earth's atmospheric pressure, hydrogen transitions from a molecular gas to a metallic state, conducting electricity the way a metal would. This metallic hydrogen layer is thought to be the source of Jupiter's enormous magnetic field, the largest of any planet in the solar system. So large that if you could see it, it would appear larger in the night sky than the full moon. What happens at the boundary between the molecular and metallic hydrogen layers? And what processes in the metallic hydrogen generate the specific structure of Jupiter's magnetic field? Remain active research questions that Juno's instruments are beginning to address. At the very center of Jupiter, gravity measurements from Juno revealed something that overturned existing interior models. Rather than a compact, distinct rocky core the size of Earth, or smaller, surrounded by fluid, Jupiter appears to have a fuzzy core, a diffuse, extended region of heavy elements mixed into the fluid envelope above it, spanning perhaps 40% of the planet's radius. This diffuse core is not what any model predicted. A sharp core can form naturally as a planet accretes from solid material that sinks to the center. A diffuse core requires something to mix that core material back up into the fluid above it. The most likely explanation is that Jupiter suffered a head-on collision with a large protoplanet early in the solar system's history, a body perhaps 10 times Earth's mass that disrupted the compact core and mixed it upward into the hydrogen envelope, creating the diffuse, eroded structure Juno measured. Jupiter, like the Moon, like Venus's retrograde rotation, like Uranus's axial tilt, may bear the permanent scar of a violent ancient collision that fundamentally changed what it became. Jupiter's 4 large Galilean moons, Io, Europa, Ganymede, and Callisto, form a system within a system, each body representing a different outcome of formation and subsequent evolution in the intense gravitational field of the largest planet in the solar system. Io is the most volcanically active body in the solar system, its interior perpetually kneaded by tidal forces from Jupiter and the gravitational resonances with Europa and Ganymede that keep its interior molten. Europa has a global subsurface ocean beneath its icy shell, possibly twice the volume of all Earth's oceans combined, with a rocky seafloor warmed by tidal heating that may support hydrothermal activity similar to Enceladus. The ESA JUICE mission, launched in 2023, is en route to the Jovian system, and NASA's Europa Clipper, launched in 2024, will make dozens of close flybys of Europa beginning in 2030, conducting the most detailed investigation of that ocean moon ever attempted. The Jovian system is, in this sense, a solar system within the solar system, a complete set of worlds ranging from the most volcanically violent to the most oceanically promising, all orbiting within the shadow of a planet that is itself one of the most complex objects in our neighborhood. The youngest thing in the solar system. Saturn's rings are one of the most beautiful structures in the solar system, and one of the most scientifically surprising in a specific way. They are almost certainly geologically young. The rings look ancient. They extend outward from Saturn to distances of 282,000 kilometers from the planet's center, spanning a volume that dwarfs the planet itself. They are composed primarily of water ice particles ranging in size from dust grains to house-sized boulders. They are visually arresting in a way that has fascinated astronomers since Galileo first observed them in 1610 and was puzzled by what appeared to be ears on either side of Saturn. But measurements made by the Cassini spacecraft during its final orbits of Saturn in 2017, when the probe deliberately dove between the rings and the planet's upper atmosphere in a maneuver called the Grand Finale, revealed that Saturn's rings are losing mass at a rate of several tons per second, as ring particles are drawn into the planet's atmosphere by Saturn's gravity and electromagnetic effects. At this rate of loss, the rings would have been significantly more massive 1 billion years ago and would disappear entirely within 300 million years. More importantly, working backward from the current mass and loss rate, the rings appear to have formed only about 100 to 400 million years ago, well after the solar system was 4 billion years old, and well after complex life had already appeared on Earth. The rings are geologically young, a temporary feature of Saturn's current appearance, rather than a primordial structure that has been there since the planet formed. This raises an immediate question. Where did they come from? A ring system the size of Saturn's requires an enormous amount of water ice, and that ice had to come from somewhere. The leading hypothesis is that a large icy moon, perhaps Titan-sized, was disrupted approximately 100 to 400 million years ago, either by a tidal breakup as it spiraled too close to Saturn, or by a catastrophic collision with another large body. This disrupted moon would have scattered its icy material into Saturn's orbital plane, where it would have spread into the ring system we see today. The timing makes the Saturn rings one of the most cosmically temporary structures we can observe. If our civilization had arisen 500 million years earlier, Saturn would have appeared unringed. If it arises 500 million years from now, if it does, Saturn's rings will be gone, and the planet will look as ringless as Jupiter or Uranus. We happen to exist at the narrow moment in time when Saturn is ringed, and the rings that have defined Saturn's visual identity for everyone who has ever looked through a telescope are a geological coincidence, not a permanent feature. The moon with an ocean and a weather system. Of all the potentially habitable environments in the solar system beyond Earth, Titan, Saturn's largest moon, offers perhaps the most alien but also the most Earth-like landscape anywhere in the outer solar system. Titan is the only moon in the solar system with a dense atmosphere, and its atmosphere is mostly nitrogen, the same gas that makes up 78% of Earth's air. It is also the only body in the solar system, other than Earth, with confirmed standing liquid on its surface. Lakes and seas of liquid methane and ethane that cover portions of the polar regions, fed by rivers of liquid methane that flow down from highland regions after methane rainfall. Part of a complete methane weather cycle that parallels Earth's water cycle in almost every structural respect. Titan has methane clouds, methane rain, methane rivers, methane lakes, and methane seas. The Huygens probe, which descended through Titan's atmosphere in 2005 and is still the furthest successful landing from Earth in history, transmitted images of a riverbed carved by methane flowing down rocky hillsides to a flat, dark plain at the landing site. Beneath Titan's icy crust, gravity measurements and electromagnetic data from Cassini suggest a global subsurface ocean of liquid water mixed with ammonia, potentially kilometers deep, kept liquid by internal heat from radioactive decay and possibly from tidal heating from Saturn's gravity. This subsurface ocean is separated from the surface methane lakes by a thick ice shell and never interacts with them directly, but its existence means that Titan may host two potentially habitable environments stacked on top of each other: a cold methane-based surface chemistry and a warmer water-based subsurface chemistry. The astrobiological interest in Titan is focused on both environments. On the surface, researchers have proposed that life could potentially use liquid methane as a solvent, the way Earth life uses water, building cell membranes from organic molecules abundant in Titan's atmosphere. In 2017, a Cornell University team proposed a specific type of cell membrane called an acetosome made from acrylonitrile that could theoretically function in liquid methane at Titan's surface temperatures of -179 degrees Celsius. Acrylonitrile has since been detected in Titan's atmosphere by ALMA telescope observations, confirming its presence, if not its biotic potential. In the subsurface ocean, if liquid water and organic compounds are present, the conditions might resemble those of early Earth's ocean. And if the same chemistry that gave rise to life on Earth could work in those conditions, Titan's ocean is a candidate. NASA's Dragonfly mission, a rotorcraft lander currently planned for arrival at Titan in 2034, will fly across Titan's surface, sampling the chemical composition of the surface at multiple locations and looking specifically for the kinds of complex organic chemistry that might indicate prebiotic or biotic processes. Dragonfly will be the first vehicle to use flight as its primary mode of exploration on another world, using Titan's dense atmosphere to fly between sampling sites in a way that no rover could do. What it finds will be among the most scientifically significant planetary data of the 21st century. Where the ocean announces itself. If Titan offers the most complex, potentially habitable environment in the outer solar system, Enceladus offers the most direct evidence that the conditions for life exist somewhere beyond Earth right now, in an accessible location, erupting into space in plumes we can fly through and sample. Enceladus is one of Saturn's smaller moons, just 504 kilometers in diameter, smaller than the United Kingdom. It orbits within Saturn's E-ring, and for decades was assumed to be a geologically dead, frozen body. Then, in 2005, the Cassini spacecraft flew close to Enceladus's south pole and detected something that changed solar system exploration forever. Enormous plumes of water vapor, ice particles, and organic compounds erupting from a system of fractures in the south polar ice. Fractures given the informal names tiger stripes, at velocities of more than 1,400 kilometers per hour. Enceladus has geysers, and those geysers are erupting material from a global subsurface ocean of liquid water that exists beneath the moon's icy shell. Subsequent Cassini flybys flew directly through the plumes and analyzed their composition, detecting water vapor, carbon dioxide, methane, hydrogen, ammonia, and complex organic molecules, including molecules with masses greater than 200 atomic mass units. Compounds that are characteristic of the kind of hydrothermal chemistry found around deep-sea hydrothermal vents on Earth, where life thrives in the absence of sunlight. The detection of molecular hydrogen in the plumes is particularly significant. On Earth, hydrogen in hydrothermal systems is produced by a reaction called serpentinization, in which hot water reacts with rock to produce hydrogen that certain microorganisms can use for energy. If the hydrogen in Enceladus's plumes is produced by serpentinization, it implies that hot water is reacting with the rocky seafloor of Enceladus's ocean, providing a potential energy source for microbial life at the ocean floor. The ingredients for habitability, liquid water, chemical energy, organic building blocks, are all present and being actively erupted into space for us to sample. The only measurement we have not made is, are there biosignatures in those plumes? Is there any chemical signature that could indicate the presence of life in Enceladus's ocean? Cassini was not designed to answer this question. Its mass spectrometer was capable of detecting organic molecules, but not of distinguishing biotic from abiotic chemistry at the level of detail needed to detect biosignatures. A future mission to Enceladus, equipped with a next-generation mass spectrometer capable of analyzing the amino acid content and chirality, the handedness that distinguishes biologically produced molecules from abiotic ones, of the plume particles, could potentially detect signs of life by flying through the plumes, without even needing to land on the moon or drill through the ice. Enceladus may be the most accessible place to look for extraterrestrial life in the solar system, and the case for sending a dedicated mission there is among the strongest in planetary science. What makes Enceladus uniquely compelling among all the candidate habitable worlds in the solar system is the combination of accessibility and completeness of evidence. Europa's ocean requires drilling through an ice shell, potentially tens of kilometers thick, to access. Titan's subsurface ocean is even more remote from the surface. Mars requires landing, sample collection, and sample return across a 7-month journey. Enceladus is actively delivering its ocean contents to space in a continuous, self-sampling plume that a spacecraft can fly through repeatedly with no drilling, no landing, and no surface operations. If life exists in Enceladus's ocean and produces even trace quantities of biological molecules, those molecules are being launched into space right now, in the plumes, waiting for an instrument sensitive enough to detect and identify them. The 2023-2032 Planetary Science Decadal Survey identified an Enceladus Orbalander mission, a spacecraft that would both orbit the moon and eventually land near the Tiger Stripe vents, to sample the freshest plume material from the surface as a high-priority future mission. If funded and built, this mission could be the one that ends the question of whether life exists beyond Earth. The plumes are erupting. The ocean is there. The question is whether we will send the right instrument in time to answer the question cleanly, before some future tidal evolution seals those vents, or the plumes change their chemistry in ways that complicate interpretation. The universe is not waiting for us to be ready. It is proceeding on its own schedule. And the window that Enceladus currently offers, a moon actively advertising its ocean in a form we can sample, is a gift of cosmic timing that the history of planetary science has not previously offered. Uranus is the solar system's most mysterious large planet, and not because of any dramatic feature. Its mystery is more fundamental, and in some ways more unsettling. We have visited it exactly once with a single flyby spacecraft, Voyager 2, in January 1986. And in the merely 4 decades since, we have sent nothing back. The result is that Uranus, the 7th planet from the Sun, is the least understood large planet in the solar system. And the data we have about it is sufficiently strange that planetary scientists have been arguing about it for decades without reaching consensus on some of its most basic properties. The most immediately striking feature of Uranus is its axial tilt of 97.77 degrees, meaning Uranus is essentially rolling on its side as it orbits the Sun. While Earth is tilted 23.5 degrees, which gives us our seasons, and even Saturn is tilted 26.7 degrees, Uranus has its poles pointing almost directly toward and away from the Sun during its orbital year. This means that one pole receives 42 years of continuous sunlight, while the other endures 42 years of polar night, and then they switch. The planet's seasons are not quarterly phenomena, but 42-year events. What knocked Uranus on its side? The leading hypothesis is an ancient giant impact, similar to those proposed for Venus's retrograde rotation and the Moon's formation, in which a large object, estimated at 1 to 3 times Earth's mass, struck Uranus during the solar system's turbulent early history and knocked the planet over. Recent models have proposed that a single impact cannot fully explain the tilt without also disrupting Uranus's moons, which orbit in the equatorial plane as expected for moons formed from the debris of a forming planet, not from impact ejecta. A newer hypothesis proposes 2 sequential impacts that could have tilted the planet while preserving the moon system. But no model is fully satisfactory, and the origin of Uranus's axial tilt remains unresolved. Uranus is also the only giant planet that does not emit significantly more heat than it receives from the Sun. Jupiter, Saturn, and Neptune all radiate roughly twice as much heat as they receive, implying large internal heat sources from residual formation heat and ongoing gravitational compression. Uranus radiates almost exactly what it receives. Its internal heat output is effectively zero by planetary standards. Why? One possibility is that the same giant impact that tilted Uranus also mixed its interior in a way that efficiently convected its primordial heat to the surface early in its history, leaving it cold today. Another possibility is that there is a layer within Uranus's interior that acts as a thermal insulator, preventing the deep interior's heat from reaching the surface. Neither explanation has been confirmed, and the absence of internal heat has implications for the structure of Uranus's interior that are directly relevant to understanding the atmospheres of ice giant exoplanets, which are now known to be among the most common planet types in the galaxy. A dedicated Uranus orbiter mission, strongly recommended by the 2023 to 2032 Planetary Science Decadal Survey as the highest priority large mission for the decade, would answer many of these questions. The mission concept currently under study by NASA, the Uranus Orbiter and Probe, would orbit Uranus for multiple years and deploy an atmospheric probe to measure the internal composition and heat flow directly. The edge of the solar system, And Planet 9, where does the solar system end? The answer depends on what definition you use. And the honest answer is that the boundary of the solar system is not a sharp line, but a gradual fading of the sun's influence into the interstellar medium. But for most practical purposes, the solar system's outer edge is defined by the Kuiper Belt, a region extending from Neptune's orbit at 30 astronomical units to about 50 astronomical units from the sun, populated by icy bodies including Pluto, Eris, Makemake, and hundreds of thousands of smaller objects. Beyond that lies the scattered disk, and further still, the Oort cloud, a vast spherical shell of icy bodies extending perhaps 1 or 2 light-years from the sun, so far out that the sun appears as just another star in the sky. But something strange is happening in the outer solar system, in the population of objects known as extreme trans-Neptunian objects. Bodies with orbits that take them far beyond Neptune and that return only rarely to the inner solar system. These objects have orbits that should, by the statistics of gravitational interactions over billions of years, be randomly oriented in every direction. Instead, a significant subset of them have orbits that are clustered, pointed in roughly the same direction in space, tilted at roughly the same angle, elongated in the same general way. The odds of this clustering occurring by chance, with the current number of known extreme trans-Neptunian objects, have been estimated at less than 1 in 1,000. Something is gravitationally hurting these objects, pulling their orbits into alignment, and the most natural explanation, proposed by Caltech astronomers Konstantin Batygin and Mike Brown in 2016, is a planet. A large, distant, as yet undiscovered planet in a highly elongated orbit, hundreds to thousands of astronomical units from the sun, with a mass estimated at 5 to 10 times Earth's. Planet 9, if it exists, would be the most important solar system discovery of the century. It would require a complete revision of models of solar system formation and evolution, because the current models do not easily explain how a planet could form or migrate to such a distant orbit without being ejected entirely. It would be visible only to the most powerful sky surveys, because at such distances from the sun, it would reflect only tiny amounts of sunlight, and would move so slowly across the sky that distinguishing it from a background star would require observations years apart. The Vera C. Rubin Observatory in Chile, which began its legacy survey of space and time in early 2025, is surveying the entire southern sky repeatedly with unprecedented depth and sensitivity. If Planet 9 exists in the southern sky, Rubin's survey will almost certainly find it within the next few years. If Rubin finds nothing, and the northern sky surveys add nothing, the clustering of extreme trans-Neptunian objects will need a different explanation. Perhaps an undiscovered population of more modest-sized objects in the outer solar system, or a different interpretation of the orbital statistics. The outer edge of the solar system, the place furthest from the sun that we could still call home, holds what may be the solar system's greatest current mystery: an entire planet, possibly larger than Earth, hiding in the dark, known only by the gravitational whisper it leaves in the orbits of the things around it. Neptune's unexplained heat, and the missing moon. Before we reach the edge, there is one more planet that deserves attention, one that was discovered not by observation, but by mathematics, and whose current behavior still does not fully match the models that describe it. Neptune, the 8th and outermost confirmed planet, was predicted to exist in 1845 and 1846 by Urbain Le Verrier and John Adams independently, both of whom calculated its expected position from the gravitational perturbations it was producing in the orbit of Uranus. When Johann Galle pointed his telescope to the predicted position on the night of September 23, 1846, Neptune was within 1 degree of where the math said it would be. It was one of the most spectacular confirmations of Newtonian mechanics ever achieved, a planet found not by looking, but by calculating. Neptune is in almost every way more extreme than Uranus. Its winds are the fastest of any planet in the solar system, reaching speeds of 2,100 kilometers per hour, faster than the speed of sound on Earth. It has a storm system called the Great Dark Spot, observed by Voyager 2 in 1989, that was comparable in size relative to the planet to Jupiter's Great Red Spot, but which had disappeared entirely by the time the Hubble Space Telescope observed Neptune a few years later. New dark spots have formed and dissipated since. Unlike Jupiter's persistent storm, Neptune's dark spots appear to be transient features that last years rather than centuries. And the reason for the difference, despite both being anticyclonic storm systems on gas giant planets, is not fully understood. Like Jupiter and Saturn, Neptune emits significantly more heat than it receives from the Sun, about 2.6 times as much. This excess heat, as in Jupiter and Saturn, is thought to come from residual formation heat and ongoing slow contraction. But Neptune presents a specific puzzle. It emits more internal heat per unit mass than Saturn does, despite being smaller and less massive. By the standard models of planetary cooling, smaller planets should cool faster and have less residual heat. Neptune's unexpectedly high heat output suggests either that its internal heat source is not purely primordial formation heat, or that there is some additional heat-generating mechanism, perhaps chemical differentiation of its interior, or tidal heating from an unknown source, that is not accounted for in current models. Neptune also had a large moon called Triton that is one of the most unusual objects in the outer solar system. Triton orbits Neptune backward, in the retrograde direction, opposite to Neptune's own rotation, and opposite to the orbital direction of all other large moons in the solar system. This immediately signals that Triton is not a native moon of Neptune, but a captured body, originally a Kuiper Belt object, or perhaps an object from a binary system that was gravitationally captured by Neptune early in the solar system's history. Triton is geologically active, with nitrogen geysers erupting from its surface detected by Voyager 2, and it has a tenuous nitrogen atmosphere. But Triton is doomed. It is slowly spiraling inward toward Neptune, losing orbital energy through tidal interactions. And in approximately 3.6 billion years, it will cross inside Neptune's Roche limit, the distance within which tidal forces exceed the gravitational self-attraction of a body, and be torn apart into a ring system. Neptune will eventually have rings that may rival Saturn's, assembled from the remains of Triton. The capture of Triton is thought to have disrupted Neptune's original moon system, scattering the native moons into eccentric or unstable orbits, or ejecting them entirely. Some of the irregular small moons of Neptune that exist today may be fragments of those original moons, broken up by the gravitational chaos that Triton's arrival caused. The solar system, even at its edges, bears the marks of a violent youth that we can still read in the orbits and compositions of the worlds that survived it. The solar system is not finished. The solar system is 4.6 billion years old, and it is not done changing. Saturn's rings are dissipating. The moon is spiraling away from Earth at 3.8 centimeters per year, imperceptibly slow by human standards, but real and measurable, a rate that tells us the moon was once much closer, raising tides tens of meters high on the young Earth, driving the tidal dissipation that also slowed Earth's rotation from a day of perhaps 6 hours to the current 24. The Earth and Moon have been in a conversation for 4.5 billion years, and the terms of that conversation are still shifting. Mars's moon Phobos is spiraling inward and will either break apart into rings or crash into Mars in about 50 million years. The Sun will exhaust its hydrogen fuel in roughly 5 billion years, expand into a red giant large enough to engulf the inner planets, and eventually shed its outer layers into a planetary nebula, while its core collapses into a white dwarf. The solar system has a future as dramatic as its past. But on the timescale of human civilization, or even of human biology, the solar system is the stable, familiar arrangement of worlds that has been our context for all of recorded history. It is the place that shaped the chemistry that built us, that gave us the moon that stabilizes our axial tilt, and with it our climate, that positioned us at exactly the right distance from a star that is neither too young and unstable, nor too old and dimming, in a region of the galaxy neither too crowded with stellar radiation, nor too empty of the heavy elements that chemistry requires. The mysteries we have visited in this documentary, the corona that defies thermodynamics, the ice on the planet closest to the sun, the twin of Earth that became a furnace, the moon made from Earth's own mantle in a collision that could have ended everything, the ocean that vanished from Mars, the storm older than every human institution, the rings that appeared within the age of the dinosaurs, the moon with two kinds of sea, the moon erupting its ocean into space for us to sample, the planet that fell on its side and never got back up, the planet whose excess heat makes no sense by our models, the captured moon that will become a ring, and the hidden planet at the edge of everything that we have not yet seen. These mysteries are not failures of science. They are science working exactly as it should. Observation producing surprise, data demanding revision, models breaking against reality and being rebuilt better. The questions multiplying faster than the answers because every answer opens a door to 3 more questions, and the doors keep opening. What makes the solar system so humbling is not its scale, though the scale is genuinely staggering. The distance from the Sun to the Oort cloud is approximately 100,000 times the distance from the Earth to the Sun, and light takes more than a year to make that journey. What makes it humbling is that we live inside it. We have lived inside it for all of human history. We have looked at it every clear night for as long as there have been human eyes to look, and we are still, in the most honest accounting, near the beginning of understanding it. The Voyager probes, launched in 1977, are now in interstellar space, the only human-made objects to have crossed the heliopause, the boundary where the sun's solar wind gives way to the interstellar medium. They are still transmitting data. They are telling us things about the boundary of the solar system that no model predicted. The interstellar medium flowing past the outer heliosphere is warmer than expected. The magnetic field orientation at the boundary is different from what the model said it should be. Even at the very edge, the solar system keeps surprising. The next great discoveries will come from the missions currently in transit. Dragonfly approaching Titan, Europa Clipper approaching Jupiter, JUICE en route to the Galilean moons, the Uranus orbiter still in planning but approaching approval, the sample return mission that will eventually bring Mars rocks to Earth laboratories, where every analytical technique developed over a century of geochemistry will be brought to bear on whether they carry the chemical whispers of ancient life. And from the sky surveys, Rubens sweeping the southern sky night after night, cataloging hundreds of millions of objects, finding the extreme trans-Neptunian objects whose orbits may finally settle the question of whether Planet 9 is real. The solar system is the place we are from. Understanding it completely is not a goal we will achieve in our lifetimes, or probably in the lifetimes of our children's children. But every observation, every flyby, every landing in sample and spectrogram and radar pulse brings us closer to an understanding of this place, our place, that would have seemed miraculous to the humans who first looked up and named the wandering lights in the night sky. We are extraordinarily lucky to be alive at the moment when the tools for this investigation have finally arrived. The next mission will find something unexpected. The next telescope will see something that doesn't fit the model. The next sample return will contain a compound that generates a decade of debate. That is not a problem. That is the adventure. The solar system is waiting, as it always has been, for us to look more closely.